So good afternoon, everyone. Welcome to the second lecture of our course on introduction to Julia. And I don't need to introduce you again to Henri Laurie, our famous lecturer for this month. Yeah. So Henri, without further ado, we all enjoyed very much your first lecture, and we are all very keen to see how the story evolves. Thank you very much.
Okay, thank you, Francesco. I hope you can see my screen very nicely.
Yeah, it's perfect.
Okay. Okay, so today is quite a technical talk. I hope I can explain things very clearly. It's about how Julia achieves a combination of dynamism and performance, and then why there is in fact tension there. So I'll base a lot of it on a paper by Besenson et al. Called Julia, Dynamism and Performance Reconciled by Design, which appeared in the proceedings of the ACM. Lionel Zubritsky is one of the co-authors. This paper appeared towards the end of 2018, but at the Julia conference of 2018, where in fact Julia version 1 was launched and Julia actually kind of publicly stabilized, he presented material from this paper, but also a few very interesting other things, which I will also draw on. So I will have to leave a lot out, obviously, as there's so much more that's going on in a computer language. What I want to explain today is this combination of easy, generic, and fast. There are a number of design aims and choices, which were largely relatively early on in Julia's development. The implementation took, in some way, some of the implementation details only really stabilized very near the launch in 2018. And that's where the speed comes from. The speed is not guaranteed. It depends on you as the programmer as well. So I want to, I'm not going to go into that in great detail, but I do want to mention a few points. Okay, so let's start with what I mentioned last week. So all functions in Julia are generic, meaning they can be extended at any time. Even when you have a particular code body for a function, the actual type signature can, if you have different type signatures, the same code body might very well be compiled to different actual callable machine code. And so that's a specialization that Julia is able to achieve. Julia has a very powerful and very detailed type system. And what this allows is very late compilation of highly optimized code. So this is what I tried to make mention of last week. And I'm trying today to present something that allows one to make a bit more sense of these claims. So I think there are three keys to the mysteries of Julia. So and they are the type system, multiple steps, and compilation sequence. So I take this to some extent from Zubritsky. There are, of course, a large number of other things, but I think these are crucial. And in Julia's implementation of its type system and its compilation sequence in particular, you get quite a lot of originality. And of course, modern languages with multiple dispatch haven't been common at all. Okay, so what I want to do now is to stop this share and go to another one. Sorry, I have to find it. Let's see if I can find it now. Yeah, there it is. Okay, so what I'm sharing here is a Jupyter notebook, and I'll refer to it from time to time again during the talk. So I'm just going to give us a few concrete reference points that people can have a sense of what I'm talking about. So I just define X and Y, and then I call on it, and I'll take away the comment. I call the plus function. So X plus Y is actually just syntactic sugar for this expression in Julia. So it's the function which has the name, the plus symbol. Remember that many Unicode characters are completely valid in Julia, and so you can use Unicode for the names of your functions, and plus is a very nice example. This macro which just tells us the actual code, sorry, I actually need to do this first. This is going to error. And it says that at this is you can see there's a GitHub link to this particular bit of code where the function for X of type T and Y of the same type T, and the T is an integer or an unsigned integer from 8 to 128 bits. Okay, so this gives us an idea of how Julia does its dispatch. It looks at the type of X and the type of Y, and it has code which is specialized depending on the type of Y. So the process, the compilation sequence, is then first the code is lowered. And what this does is it just is a simple presentation of the process in an abstract syntax tree, obviously in this case extremely simple. And then this lowered code is annotated with types. This is not actually a simple process because it involves type inference depending on every line in the code body. Of course, yeah, there is no real thing to do. So it basically says the output is known at this point to be int64. Sorry, this register is known to contain int64 and the return is int64. And so this is then turned into the LLVM representation of this particular thing, which LLVM can then turn into assembly for sending to the final machine code. So if we use different types, for instance, if we make this 2.0 and we make this 3.0, then now we see that it's again of the same type, but the type is now one. It's now a union. It's now one of these three floating point types. So there is also a big float type, but it's not covered by this particular code body at line 383 of float.jl. And this lowers in much the same way, and it types in much the same way, except of course that it now add float, not an integer. And instead of add I64, we have f add double. And so this is the sort of thing that if you write code in statically typed languages, you will be quite comfortable with these type annotations. And if you ever looked at your compiled code, you would actually do much the same thing. If we look at that, we see that it's just still two actual instructions that are going to be used at the machine level. If we actually do things slightly differently, let's say we make this a 3 and this a 2. So now we have mixed type. This one is a floating point number. This is an integer. And so if we ask for what code body we get that, it comes in under promotion. And it's X is a number and Y is a number. And it's not required that they're the same type of number. They will be promoted to a common type. And then the addition will be carried out. So when you lower it, you see there's a promote. And then this core.apply iterates. It's a bit odd because there are only two numbers, but it's an iteration. And if we look at the typing, Then we see, actually, we don't need to apply iterate. We can just add float because we promote y to being a floating point number. So the 3 is turned into a floating point number. And the LLVM is still very simple. There are now 3 instructions, and likely, similarly, there are 3 instructions there. So this is all very simple. I don't really have enough time to indicate what happens if you use these other items. One of the interesting things is that whether you use 8, 16, 32, or 64-bit unsigned integers, the machine code looks exactly the same. But when you move to 128 bits, the machine code looks different. And obviously, this is because on my laptop anyway, it's possible to just use one addition instruction because these ones all get padded out with zeros to 64-bit numbers for the purposes of the addition. If you want to take advantage of shorter integers, then I guess you start going on to GPUs. Okay, so I don't want to go to world age yet, so I'll stop this share and I'll go back to the presentation. So that was the demo, and I was just trying to show how multiple dispatch and the various types start working together, and something of the compilation sequence. Okay, so now I want to answer the question, why easy, why generic, why fast? Why is Julia easy? That's actually quite an obvious answer. It's a modern dynamic language. It has a runtime. It has lots of utilities that are available in very few lines of code. You don't have to do any memory management. And there's a very clear syntax which draws on decades of experience on what not to do. And in this, of course, it resembles many dynamic languages with these properties. So it's not surprising that it's easy because there's so much to draw on. What is it that makes Julia generic? First, the functions are generic. You can always add another method. So that means that it's very easy to get new functions all the time. Of course, we're very familiar with that. But there's another aspect, which is the abstractions that are available to you via the type system. And this is not something that is so easy to explain. It is something that one kind of experiences when you do use Julia, but you don't necessarily very consciously make use of it. The point of this abstraction is how you can extend the type system. And because there are these various layers of abstraction, when you extend the type system with your own new types, you can decide where they fit into the type system, at what level and at what level of abstraction. And these things combine in the following way, that if you have existing types and you have new functions, it's actually the new functions just can be just to work with the existing types. They don't have to be put inside anything else. It's relatively simple to make sure that they use that they work for existing types. Similarly, if you have new types, it's relatively simple to make sure that existing functions can actually make use of the new types. And so I will come back to that later, I think. Okay, so what makes Julia fast? Okay, so this is the bulk of what I'm going to talk about today. And the real point is actually that one expects Julia to be slow. So a compiler should not be able to optimize the code from a dynamic language particularly efficiently because of the nature of the dynamism means that the code is liable to change at any time. And so the compiler has to has to be ready to accept very many different modifications to the code, and the assumptions necessary for optimization are therefore not satisfied. When I say fast, that is of course set by the actual system and the algorithm that you're using. So it's only relative to some basically some top speed that we're talking about. The habit in the Julia literature is to compare Julia to a top speed achieved by C. And then Julia beats C from time to time. So it's not actually, it's a pretty relative measure. Anyway, the question is, why is Julia not slow? Okay, so if I were to again go back to Lionel Zubritsky, then the dynamism, although the dynamism is there, it is constrained. And so many of the difficulties that the other dynamic languages impose on the compiler are avoided. The type system then is sufficiently powerful to get very good instructions to the compiler for the sake of optimization. And this includes the fact that concrete types have no subtypes and that all types are parametric, which I'll also get back to. And the final point of the speed is that you get these specialized code bodies for each unique type signature. And if you get all of this right, then you get it fast. And that is what I really need to explain. Okay, so let's start with the aims that the Julia designers have and the choices they made. So the first design aim was that the glue code and the performant code are in the same language. And that was a very powerful motivation for the three young people in the project. That is Besenson, Karpinski, and Shah. I'm not quite sure what Alan Edelman felt about this, but he's not quite as publicly visible when in publicizing Julia as the other three are. The idea of glue code and performant code comes from the late 90s, in particular that Oosterhout paper that I mentioned last week. So the idea is that you can just make pieces of your project in highly performant code and then glue them together by usually some dynamic language. So this is a convenient language within which to experiment and within which to write short bits of code that is very quick to write. And you just get the glue code and the performant code together in this way. And the problem with that is that to get two pieces of performant code to perform, to also in their performance together to work very well, turned out to be very difficult. If you have them in the same language, they're all at the same speed, and this issue simply doesn't arise. So that was the first design aim. The second aim was just dynamism, and that was because people like working in a dynamic workflow. And the third one that they wanted was the code introspection. In this case, because of the individual histories, I think they were very much wanting to do code introspection in terms of the Lisp tradition. So the choices they made, I don't know about the syntax. It looks a lot like Python and MATLAB. It works, but I don't know the history. So the first and most important choice probably is multiple dispatch. There was some dispute. You can get hold of some of the, in particular, the launch talk 2018. The early emails, some of the early emails are shown. Multiple dispatch was a very early design choice, especially because it was felt to be very suitable to numerical work. The second design choice that came up early was specialized and late compilation. So that was just at that point, it wasn't necessarily at all clear how to achieve it. but it was just said that that is a very worthwhile choice to go for. And I think that what that meant were the two following implications. So they're also choices, but I think they were kind of forced by the first two. The one is that all functions are generic. And the second thing is that you have a complex type system and a simple object model. I'll get to exactly what I mean by that. Okay, so still with design aims and choices, there are some implications of dynamism and code introspection, which I want to get to. The first is the obvious implication of a dynamic language, is that you have to have a runtime, which will do parsing and dispatching and interpreting and basically enable all the interaction you want in your dynamism. But if you also add code introspection, then there is a danger that a function might change itself. So in particular in Julia, there are macros and there are eval and a number of other introspection devices, which actually might kind of attempt to change the way a function works in the middle of its run. And that in itself is not necessarily a bad thing, but it really interferes with code optimization. And you have to then keep going back to the runtime, keep going back to some kind of dynamic dispatching, keep redoing things. So the chances, if you allow macros in eval too much free rein, they are going to make the language very slow. And so the Julia solution is following. First, macros are not runtime things. They are expanded very early on in the compilation cycle, the compilation sequence, and they are purely syntactic. They do nothing else. So that makes them very easy to reason about, and it also makes them relatively harmless. The second thing is that eval is done in global scope, but this is not a trivial remark. I certainly don't know if I could explain it even about a lot of time. So I will just note that this constrains eval to what it does. And in particular, usually a function cannot change itself by running eval. And then the third thing is the world age. So this, as I understand it, is a Julia innovation. There's an interesting paper by Beljakova et al., which claims that world age does not have to be unique to Julia. Many other languages have features that should allow them to introduce world age, and in this way protect code from being changed on the fly. And so what that means is that during compilation, the whole parsing sequence, the whole compilation sequence can make much better inferences because of this thing of world age. So I want to again go to the notebook and just give a very brief taste of what world age means. Okay. So this is Stefan Karpinski, one of the founders. And there's just in the Julia discourse, there's a discussion of world age. And he weighs in and says, look, if you want a really simple example, then this is what you can do. So we define a function f. It doesn't take any argument, it just outputs the value 1. And we put it in a wrapper G. But inside the wrapper G, we now change the function, we redefine f to output the value 2, and then we call f. Okay, so let me compile that. So now there's a generic function G, there's also a generic function f. And now I'm going to call this twice. I'm going to put it inside a tuple, that's the outside parentheses, and I'm going to call G once, and then I'm going to call G again. And the interesting thing is that the values are different. So the first time this runs, so when I did the compilation, f received a world age, and G received a world age. And then F was recompiled and it received another world age, which is younger than this one. And so when this F was called, this young world age wasn't used because it was too young. And instead this one was used, and that was why this call to F used the first compilation. But that actually took things to the end of G back to the top level. So the second time it got called, the F was no longer too young here, and this recompilation was the second value. If I use the invoke latest function, which makes it slower and introduces the dangers that I spoke about, then I can force it to use, for when I invoke here, I use this more recent definition of F. And so if I execute that and then run G twice, I get 2 both times. So that's a rough idea of how world age works. And the basic point is to get functions, to make sure that functions don't interfere with themselves.
Henri, sorry to interrupt. There is a raised hand by Stefan Lotz, and I will just give him now the right to ask the question in person. So Stefan, please, you're welcome to ask your question.
Thank you.
Hello, Stefan.
Hi, sorry.
Hi.
Can you hear me?
Yeah, I can hear you.
Yes.
Okay. So I just want to get wrap my head around this. So it's like when you executed G the first time and then the second time, it's like that evaluation of F sort of.
Your sound is very poor. I'm not quite sure why I'm not hearing you.
I don't know, either it's my headphones that's messing up now.
Okay. Please repeat.
Anyway, see if I can ask the
Stefan, in order not to interrupt too much the flow, you're welcome to type your questions in the Q&A.
I'll do that. I will do that. No problem.
Thank you.
Okay.
Okay, but I'm going to stop the share now, and I can come back to it if there's time to, when the question is clear.
Yeah, perfect. Thank you. Sorry.
Okay. Yeah, so the world age issue is to enable very good reasoning by the compiler about functions. So the compiler needs to know at compile time that the function is not going to change in the course of the compilation, and so that it has certainty about what actually the function is. And in particular, when there are numerous functions being called, that all of them are stable in that sense. Stability is another term I'll come back to. Okay. The other aspect of the design and the choices that I want to emphasize is the type system. So I've mentioned that there's a very simple object model, and there's a little bit of metadata, it's not very detailed. And for the rest, the object is just the actual data that a value contains. So basically, objects and values in Julia seem to be more or less interchangeable, what the terms refer to. But the thing is that every object must have a type. There may be more metadata, but it must at least have a type. And the type system, the various types, are a strict tree, so there's no cycles in it at all. The concrete types are the leaves of the tree. Every other node is an abstract type. And what that means is that underneath a given abstract type, there is a set of leaves that belong to that particular abstract type. And as you get more and more abstract, you may have larger sets of leaves. Okay, so it's perhaps not entirely clear from the foregoing, so I will emphasize that an object must have a concrete type. So it's data, so it's actually bits of voltages and inside the physical reality of the computer. They're concretely existing data, and they have a given type. And all values that Julia uses to compute are of concrete type. I should add, though, that a type itself, not the type annotation of the data, but the type, let's say a type like float 64, that is something that also exists in data. It's specified that float 64 is 64 bits and so on. And so that can be computed with. As I said, some types are primitive. They have a specified length in bits, so 64 bits or a 64-bit integer or a 64-bit floating point number. The character data type and the unsigned 8-bit integer data type, both are 8 bits long. It's just that when a function when a function is written for something that is a character, then it interprets these 8 bits as referring to some Unicode, some bit of Unicode. You can combine various types by putting them either in a mutable or an immutable combination, and there are their keywords. And most of the time, if you write your own code and you're making types, you will use one of these two to construct your types. Although there's nothing stopping you from defining a new primitive type and defining functions that use it and so on. An interesting thing about composite types is that they may have 0 fields. So they may contain no data at all. So the composite type is not defined any further than its existence. Or else if there's one or more fields, they each have to have a name. What is further interesting is the parameterization of functions. And here's an indication of how it might work. So vector is a type, but it's neither a concrete type nor an abstract type. So it's not actually in the type tree. What is in the type tree is a type called abstract vector. Vector is then a subtype of this, but in order really to be a subtype, it has to have a parameter. So this is a vector of all of the elements of the vector are of type signed integer with 8 bits. If you say you have a vector and you allow anything, strings or functions or characters, whatever, then it would again be a concrete, well, yeah, I guess I'm not quite sure, vector of type any, I think, yeah, I'm puzzled now by that. I'm not so familiar with all the parameterizations of types. Furthermore, when you have several types, you can make them into a union. And this may not be a union that corresponds to one particular set of leaf types that sits under a given abstract type, one of the nodes in the type tree. So you can basically make ad hoc abstract types by making them into unions. So these two, the parameterization and the unions, means that the type system actually is not merely extendable, but it's kind of almost dynamic by itself. So this is quite a complicated thing to get used to. And if you look at Julia code, these aspects get used again and again and again. But once you actually start understanding how the type system works, then it starts to feel quite natural. Okay, so the idea behind this is just 3 things. I'm now moving on to the implementation and why that enables speed. devirtualization, inlining, and unboxing. So these are quite technical things, and it's, I think, to present them succinctly and in a mathematically respectable way requires quite a bit of computer science. So what I will do instead is I will again go to some work by Lionel Zubritsky and just go through his example. Oh, maybe let me just check the chat. How is world age defined? Okay, Stefan, world age is just an integer that keeps increasing. It actually increases, it corresponds to the state of the global system, I understand. And so when you go inside a function, like as inside G to recompile F, once we go inside G and we recompile, we have a new thing that increases the global age. And so the functions, the recompilation are then of a greater age. But once we go back up to the function, then F is actually is at the once we've called G once, then that is when the compilation happens, is when we call G. It's not done just because G is compiled. It only happens when G is called, and that recompilation is therefore younger. But then that has all been done. It's not repeated. You don't recompile. The compilation has been done once, then you just reuse what you've got. So when you call G later times, there's no recompilation of F. Does that make sense? Is that good enough? Okay, thanks. Okay, so let me go to the Zubritsky example of devirtualization, inlining, and the requirement of type stability. Okay, so here we have 42. This obviously is inspired by Douglas Adams. X has the value 1 if we're looking at life, the universe, and everything. And here's a function that blocks type inference. It actually seems to be always possible to block type inference, but in a discussion I've been having with Zubritsky himself and also Kino Fischer, one of the main people in writing the internals of Julia, this way of blocking type inference isn't necessarily going to be the most important, and the type penalty, the speed penalty you pay isn't the same for every way of blocking type inference, but this is a convenient way of blocking type inference, and so I'll just keep on using this. And now these are just two different wrappers. In the first one, foo is able to use the type of X because it's operating on Y, which is just an alias for X. But in the second one, Y is not able to carry the type information of X. And so when you do foo of Y here, you cannot use the type information of X to do type inference. So although X is a value, it's a concrete value, it has a type, the type cannot actually be used because the time of using the, I don't know, it's quite technical, I'm not going to go into it. And I compile these two. Let me first just not optimize, just see what happens if we do the type code typing. So this optimize refers to a particular stage in the compilation sequence. So this gives the typing before any optimization is done. And you can see that if we don't optimize, then we just note that we have to apply main.foo to the function y. And that is much the same for both of them. The only difference is that here, because the type inference can be done, it can be inferred that the output is an integer because it's 42 times an integer. It must be an integer, but here it has been removed, and so you don't know. And so it's 42 times something. It can be of type any, because it could be 42 times a character, which will give you a string of 42 repeats of that character. 42 times character. No, I'm not quite sure what it would give you. Let's see what happens if we turn the optimization on. I'm going to do it on both of them and then compare them. And now we see that if the optimization is done here, then it's done on X, no longer done on Y. So we can directly use the value X, and we can directly multiply. So what happens is that foo has actually disappeared. The foo has been devirtualized, and it's been replaced by something very efficient. So that's not necessarily inlining, it's actually a replacement, but this is where you might be able to do inlining if everything was statically known and effectively equivalent to static compilation. But in this case, there's nothing to do. We still just stay with foo. Foo could be any code. And I want to run that one first. So now we see that after optimization, the node type must still use foo, but the first one can just use multiplication of integers. And so the first one ends up with just 2 machine instructions, IMLQ and redq. But let's look at what the second one does. So it has very, very many more machine instructions, and many of them are allocations, moving things around, pushing them, and so on. So these are expensive, they take time. So this is going to be very, very, very much slower than the other one. Okay, back to the, so I just put that in to give an example of why, if you can do these things, then they are fast. So I haven't spoken about unboxing. That's also something quite special to Julia. What it allows you to do is, if you have a vector of all of them are, say, of floating point numbers, instead of dealing with a floating point with each of them as a number of type floating point and keeping them boxed, you can just say, here's a sequence of numbers. All of them are floating point numbers of known size, so they all float 64. And so you can just zip through the whole lot very quickly. And these are, I think, a very large part of why code written in Julia, when it's written properly, looks almost very similar to code written in C. Okay, so this is what I'm saying. The implementation enables speed because it enables especially these things. So let's see what the type system does. So the type system in multiple dispatch has a relatively clear item. Because it's a tree, there's a partial order on every type. And what that means is that when we have type signatures, so now there are several types in a type signature, we can compare these type signatures for specificity. and then the most specific one can be chosen. In practice, that requires heuristics because the trying to write an algorithm which will absolutely choose the single best one every single time is very costly, and the heuristics almost always get it right. Okay, so now again, I want to go back to the Jupyter Notebook, and so let me remind you what happens here. The type 2 and 3.0 is not explicitly a method in the list of methods for plus. What there is instead is this abstract specification of code. And so this relies on 2 being promoted to 3, then they're both, so when they're both of type number, the first thing is to promote them so that they are of compatible type, and then to execute them. Most integers can be represented approximately as floating point numbers, and so the choice is to promote the integer to the floating point number. But obviously, this might involve some approximation, which you may or may not like to do. Okay, so let me go through this example. I define a function f1. I say the first variable, the first value in the argument must be a leaf type that sits somewhere under the abstract type real, and the second one must sit somewhere under the abstract type integer. And if I give it 1 and 1, then 1 sits under the integer 1 sits under real, the integer 1 sits under integer, and so it just gives us 2. I can, in fact, make the second one. I can make this a 1.0, and then x is a real and y is an integer. And then, because of the rules of promotion that I mentioned previously, the integer will be promoted to a real node, to a fixed point number, and the addition will happen. Let's look at what happens with the, if we type the code, we see that there's first the promotion and then the addition. Now, suppose I define a function f, and I give 2 definitions. The x and the y is integer real or real integer. But if you have x an integer and y a real, then you multiply, and you have x a real and y an integer, then you add. I have the f without argument that we had from before, and these 2 new methods. And so now there are 3 methods for this multifunction. Let me call this for 1, 1. And before we do that, just think for a moment, what do we expect to happen? The type signature is 1, 1. So those are 2 concrete. 1 is under real and under integer. 1 is under integer and under real. And the effect is that there is ambiguous. There are 2 function signatures which satisfy this. And so it's not possible to choose between them. So this heuristic doesn't always work. It's not a guarantee that the specificity will give you exactly 1. It's not a guarantee that there will be any code body that fits your particular your type signature. So this is definitely a possible source of difficulty in coding. It's something that, as an expert programmer, you learn how to deal with, how to avoid. like any language, you have to learn what are the likely bugs that you are going to encounter and how to protect yourself against it. Okay. So very quickly, let me go through the type system in the compilation sequence. There's only one place. You adorn the lowered code with types. And in order to do that, you step through the code line by line. And at every line, you look at all the values and you check whether any of them change type. There are many operations that do change type. Just think of dividing an integer by another integer, or then the result has to be a floating point number because you do not know whether you get an exact division or not. So when that happens, the resulting value you get might be known only up to a union of types. For instance, if you have an integer, you divide by 2, you certainly get a float. But if you're in a loop and let's say you have an integer n and the n keeps changing, then that n could be either an integer or a float, and so it's known only to be one of the two, an integer or a float. So it's in a union of types, and that means it's an abstract type. So once you have widened once you've enlarged the set to which you know for certain that a particular value belongs, you have to propagate this back to all the places where this might play a role. And you have to go through your code body maybe several times to make sure that you've actually finally, that the abstract values, the things that you've assigned are now stable, and then you can say, okay, now the code is typed. So if only concrete types occur in the typed code, then the compiler can optimize, can emit efficient code. And the term used in the Julia community is a code stable. If a function is code stable, it means that the compiler can reason very accurately about the code, and it can deal with concrete types at all times. In order to enable this kind of behavior, there are a number of things that is required from the Julia programmer, which I will call Julian style. The first is that instead of a few large, long functions, you break up as far as possible into many short functions. That makes it, for the human being, easy to reason about, but also for the compiler. So you're much more likely to get type-stable code if you use short functions. That is, of course, the point is to get type stability. So that's really what you have to work towards. And Julia has a number of tools that help you to check the type stability of your functions and your function calls. There is a way of organizing namespaces, and in particular, kind of structuring where your eval function is in global scope, which is called modules. And it's actually very useful to do that even for small projects. And one of the things it allows you to do is to really minimize the amount of top-level expressions you have, because that is what the compiler finds the most difficult to reason about. Similarly, to avoid globals, because they sit in the top level. Avoiding allocations is, of course, a general thing that one should do to get speed. But in Julia, allocations might be hidden, so it becomes quite a skill to avoid them. And you should use explicit loops. So that was one of the most interesting things for me to learn as a Julia coder. It's just to get rid of vectorization. However, in recent years, there's a code convention in Julia called broadcasting. And it allows you to, instead of saying A plus B, where A plus B are vectors, and you then have to loop over every element of A and B and add them one by one to get the result. instead, you can just say A dot plus B. So it looks very like vectorized code. But what happens under the hood is that Julian unrolls the broadcasting into loops. You should be extending the type system with your own types, because that helps the specialization of compilation and helps efficient choosing of dispatch. Julia is using dispatch all the time, so the more efficient you can make dispatch, usually that will help with speed. There's a thing called type piracy that you have to avoid. I can't get into that. And continuous testing. Actually, this, of course, is something that applies to any coding project. But in Julia, it's particularly easy to keep testing exhaustively because you're doing high performance work, but you have a very convenient interactive dynamic context in which you do that. So it's easy to test exhaustively, and it's therefore easy to look where your pinch points are. The linting and the profiling in Julia is not that mature, but certainly people are using it all the time, and it actually, the proof of the pudding is in the speed that Julia has been achieving. Okay, so that's the summary. Easy is to be expected. The genericity comes from multiple dispatch plus type abstractions. It's fast because of the concrete type inference on function code bodies, provided that they're type stable, and it can avoid boxing. And so the LLVM optimizes very well. And then there's a bonus, which is that code composition works very well in Julia, and that enables a very high level of reuse. And I will talk more about that on September the 28th. And let's see, next week, I'm going to focus on this project, differential equations. It's a real flagship for me personally. It's most of my experience in Julia has been with this package, or rather meta package. And it's an incredibly successful suite of software. So I think it's very worth looking at why they succeeded and what they did. And then the last week, I want to get back to the question of one language, just one language for an entire project. And then you get massive code reuse and very rapid development. I would say the answer is yes. And the rapid development is because of the first two items that can be done. And maybe open up the question of whether this make Julia very suitable for high performance computing or not. Which I'm not enough of an expert to say, but I think it's a very interesting possibility. So that's me done.
Yeah, Henri, thank you so much. It was another fantastic lecture, and it's really gripping this Julia mania. So I'm sure we will all be Julia enthusiasts immediately. Yeah. We had already, no, thank you very much. I really enjoyed it. In particular, your style of telling us also the background stories. Yeah, not just the MATLAB or Python-like commands. Yeah, that's the easy part. But it's really nice to understand the whole philosophy behind Julia. That's really very nice. Thank you so much. I really appreciate that.
It's a real pleasure.